Hey, I wonder if there's any students. Yeah, we got Ryan. There's one right there. And Nicholas. Yeah. So we're gonna have a class. Good deal. And Ashley. Yeah. Somebody say hi.
Good morning.
Good morning. Good morning. Tomorrow is the first day of fall. Did you know that?
No,
Well,
I
that's what
didn't.
my calendar says.
Yeah, that's about right. The end of September.
Yeah, it's gonna be fall tomorrow. And Stuart's with us. Yay. Picking on Stuart for something. And Mark and Braxton. We've got a good crowd. But class hasn't, Shane is here. But we have 1 minute before class. Do you guys have any comment or question before we begin? Well, let's see if I can adjust this. Needs to be down or something. Let's see. Yeah, that's not too bad. Yeah, there we go. And wait a minute. Do I need to move this over like, yeah, there we go. That's pretty good. Okay, well, today's topic is Newton's second law. The most important equation in our course. But today we're studying Newton's second law in the normal tangential coordinate system. Let me refresh your memories about the equations there. The way it works is the velocity is equal to the vector velocity is equal to the magnitude of your velocity times a unit vector in the tangential direction. I wonder if I'm writing that big enough. Yeah, let me see if I can write bigger. See the velocity vector is equal to the magnitude of the velocity vector times the tangential unit vector. And the acceleration vector is equal to the acceleration vector is equal to that. See, this is the tangential component of the acceleration. Some people call that the speed. And this is the normal component of the acceleration. And some people call that the radial acceleration. If you're going in a circle, some people call that the centripetal acceleration. I know you've heard that before, centripetal acceleration. I think we derived that from scratch one day, but I'm not sure. I don't remember. Seems like we did. But that's our topic today. And we're going to work some problems and have some fun. And you have homework. And let me look at the homework here. It says the homework, today's the 21st. You have a problem that's your homework. It's number 10. I believe it's homework a problem assignment number 10, and it's problem F 13.8. Is that what this says? Yeah, it's on page 145, and it's due the 24th. Now, when is the 24th? Would that be that'd be Thursday? I've got a calendar here, and it says, yeah, that's Thursday. Okay. That's Thursday. All right. Now, did you guys have a test? I think you did. Did I grade it and give you some? Yeah, everybody took it. And I've got exam 1 grades for everybody, and it should be posted on the Blackboard. Yeah. Okay, well, we're gonna have fun now, but do you have any questions for me before we begin? Okay, well then let's just do some problems. I wanted to do a problem here. This is totally organized here. This is problem F1311. Yeah, let's do that. So I'm going to erase all this stuff. These equations are in the front flap of your book. I think they write them a little differently, though. Instead of writing it like this, they'll say A with a little t on it equals V dot. I think that's how the book writes it. And this here, they'll say A with a little n on it underneath it there is equal to this here. They're just saying the same thing. This here is called the tangential, or you could say the tangential component of the acceleration, and this is the normal acceleration, or you could say the normal component. Okay, what did I just say? I was going to do a problem, and I forgot what I was going to do. It was an F problem. Yeah, it was problem F 1311 maybe. Page 145. Let me find it here. Yeah, let's do that. That'd be good. Okay, I'm going to erase all this unless you had a question. Any question? Okay, we're going to erase all this. And we're going to start with problem F1311. And it's on page 145. And you know the drill. You draw a free body diagram. Okay, here goes. We're going to draw a free body diagram. It says there, a 10 kilogram ball. It's at 45 degrees. 45 degrees. 10 kilogram. It's hanging by a string there. Having a little trouble here. This is supposed to be 45 degrees. You know, I didn't measure that. That's too small. You know what? That's not 45 degrees. No, it's more like 40. It's not too bad, really. But here, let's make it 45 degrees. Here we go. There, now I kind of measured that or tried to. And it says it has a velocity of 3 meters a second. Okay. Well, let's see, it's got a velocity of 3 meters a second. And what else do we know? Oh, this is 2 meters. This string here is 2 meters long. Okay. What else do we know? Determine that we want to find the tension in the cord and the increase in speed of the ball at this position. What they want us to find is the tension in the cord and the increase in speed of the ball. You know what that is? That's your tangential acceleration. That's what they want you to find, the tangential acceleration. Okay, well, we're going to do it. But before you can do it, I'm going to have to call on one of my excellent students here to help us. We have got to have the directions. We've got to have the tangential direction and the, what's the other one? The normal direction. So let me pick on one of my wonderful students here. And let's find, here we go. William, unmute and say hi, William.
Hi.
Hi, good going, William. William, we have to put these unit vectors here at the body. That's our body right there. And I've got my green pencil here, and I'm gonna write those unit vectors in. And William's gonna tell, where do I put this UT, William? Where does it go?
UT goes along the direction of motion.
That's it. He knows. Here, I'm gonna draw it for you. There you go. There's your UT. Here, let's make a note of that. This direction is in, like William said, it's in the direction of your motion. Some people say it's in the direction of your velocity. Some people say it's in the direction of the path. See, the path that this thing is following is a circular, it's kind of going in a circle. That's the path. Good going, William. Now, as long as I've got William, I need the direction of the normal unit vector. Help me on this, William. Where does it go?
That'll be perpendicular to the tangential unit vector.
Yeah. But which way is it going? Up or down?
Oh, back towards the center.
Yeah. There it is. There's the normal unit vector. It's always in the inside of the curve. See, there's a curve here. I don't know if you can see those dashed lines, but this thing is going in a curve. See, it's going kind of like a part of a circle there. and it's the inside of the circle. Okay, thank you, William. He knows what he's doing, see? So we're off to a great start. Now to find the tension, what we're going to use is Newton's second law. Only we're going to write it like this. We're going to write it in the components of the normal direction. And thanks to William, we know the normal direction. And see, I forgot to put my forces in red. Get a red pencil, put your forces in red. See, here's your tension. It's pulling on that ball there. And then here's your weight. And that would be 10 times 9.81. You know what that is? That's 98.1 newtons. So we have, that's it, guys. There's just the two forces. And what we need to write is the normal components of those. Well, need a little room here. The normal component of that tension is just the tension. It's entirely in the normal. It's in the normal direction. See, going the same way. See, there's the normal unit vector. There's the tension. But now the weight here has a component. It's kind of coming down this way. And in the normal direction, it's going negative 98.1 newtons times, we need this angle. Well, that angle would be 45. You know what? I think so. That's 45 up there. Would this angle be 45? And well, I don't know. We know there's a 45 here too. Does that help any? Yeah, look here. If this is 45, this is the same angle. Look, it's the same angle. Yeah, so it's 45. So you're going 98.1 cosine of 45 equals 10 kilograms times V squared over R, is that right? Yeah, 3 squared over 2. You're supposed to put in units, so maybe I should. 3 meters per second. There's your equation. Now I'm going to shut up for a minute, and I want you to plug this in and get the tension. And then I'll call on one of my excellent students, and we'll see if we get it right. We got an equation. There's only one unknown. Look, only one unknown. The tension. On your mark, get set, go. Okay, I'm always picking on Stuart. Stuart, do you have that yet?
I got 114.37.
That's what I got. The tension's 114.37 newtons. Stuart got it right. We did great. Now they wanted something else. I forget. Was it? They wanted the tangential acceleration, I think. Let me read this. Yeah, the increase in speed of the ball. That's what that is. Okay. Now to get that, first of all, though, is there Anybody having a problem with that? Well, I guess not. I guess you're okay. All right. Now to get that, what we got to do is we got to write the Newton's second law. But we're going to do it in the tangential direction. Okay. Well, let's see, where's the tangential direction? Well, thanks to one of my excellent students. Dang, who was that? Short-term memory problems here, guys. One of my excellent students showed us the tangential direction was in the direction of the velocity there. And we've got to get the components of the forces. There's only two forces. Hey, you know what? That tension doesn't have any component in the tangential direction. It's perpendicular, but this one does. I need a little room to write here. Let me sacrifice some of this here. There's a component in the tangential direction of that weight of 98.1. It's right here. Cosine 45 degrees. And that's it. Equals to the mass, which is 10 kilograms times v dot. That's what the tangential acceleration is. It's v dot. Okay, let me do that. All right, I'm doing that. Well, I got an answer for what it is it's the how did they put it, the rate of change of your speed, is that what they call it? The increase in speed, that's what they call it. What it is the tangential acceleration, and what I'm getting is 6.9 blah blah blah. Okay, ta-da, we just finished it. Let's see if we got what they got. Go to the back and help me find this. This was F1311. F1311. This is 114. Yay, that's what we said. We said 114 for the tension. And they said the A sub T is 6.94. That's what we got. We got 6.94 if you rounded it up. We did that good. Well, that was good. Wasn't that fun? Did you understand it? Did anyone have a question on that? Okay, well then let's do another one then. Okay. If you understood it, great. We'll do another one. I'm going to erase this unless you speak up. We are studying Newton's second law. But what we did was we broke Newton's second law into normal and tangential components. All right. Okay, well, let's do this one here now. I wanted to do F1310. F1310. Now this is on page 145. That's what same page that other one was on. And there's a car there. Here I'll try to draw this car. Here we go. And they said that there's a 30-degree ramp. All right, well here, I'm gonna actually measure 30 degrees. We're gonna get this 30 degrees, just like they said here. Okay, 30 is right here. All right. Do you do your stuff? Do you carefully measure your stuff? You're supposed to. Ta-da. There, see, I actually measured that. There's an angle here of 30 degrees. Now there's a car here. I think I see the headlights. It looks like the car is coming at us. So it's kind of hard for me to draw a car doing that. There's his headlights. Put a driver in there. Obviously, United States. See, because if this was in England, the driver's over on the other side. Did you know that the steering wheel's over on the other side, on the right side, on those English cars, and then they drive on the other side of the road too. I don't know if you've ever been to a country like that where they drive on a different side of the road, but the cars have the steering wheel on a different side. Unmute and tell me if you've ever been in a country like that. Anybody out there? Nobody. Nobody's ever gone any place. I bet you have. You're just too shy to speak up. Okay, well, here comes this car. Now, let me write this. It says here it's going in a circle. Well, no, it's banked. It has a radius of curvature. We could pretend it's going in a circle. And the radius of the circle is 500 feet. So here, let me draw that for you. Here we go. We're going to put 500 feet here. We could just say he's going in a 500 foot. Do you understand? He's coming out at you. And he's going around in a big circle. He's going around, going back behind the board, coming back around in a big circle, and he's coming at you. He's going around and around. Keep reading. Curvature 500 feet. Coefficient of static friction is 0.2. Let me write that down. Mu sub s is 0.2. Determine the maximum safe speed so no slipping occurs. Neglect the size of the car. Well, man, that's all we know. Okay. I think we got all the info. I need to talk to you about this friction business. See, the way it works is, we'll talk about friction for a minute. We'll get back to a problem. The coefficient of static friction is less than or equal to mu sub s times the normal. I know you've seen that before. And mu sub s is 0.2. Now, it's equal to that. It's equal to that if you've got the maximum possible. Then it's equal. You no longer have an inequality. They have a name for that. They call it impending motion. I don't know if you've ever heard this before. But impending motion is when you just exceed the static friction and you start moving in that direction that friction's keeping you from moving. And then you've got kinetic friction. Now the equation for kinetic friction goes like this. It's not an inequality. It's an equality. But the coefficient of kinetic friction is always less than the coefficient of static friction. Hopefully I'm boring you because you know all this. Now, they did not give us the coefficient of kinetic friction, but let's just make one up. It's probably something like maybe 0.1. It's always less than the static friction. Let me see if I can explain this. If you go into your kitchen and take a kitchen chair, here's your chair. There you go. Artist's rendition of your kitchen chair. There. Yeah. Okay. There we go. And just grab it and gently push. Well, it won't go anyplace if you push very, very gently. And now increase the push, not much, but increase it just a little bit, and it still won't go anyplace. But if you continue to give it just a little more pressure, increase your force on that chair gently. Oh, then it will move. You have just gone from impending motion to motion, and you have gone from static friction. See, while you gave it a very gentle push, this is less than. And then when you reach the place of impending motion, this is equal to. And then when you break the static friction and the chair starts to slide across the kitchen floor, then you've entered the world of kinetic friction. Hopefully you knew all that, and I'm boring you. See, what we're doing here is, if this car goes faster and faster and faster, it will slide up the hill. See, he's coming out at you. He's going around in a big circle. Or at least he has a radius of curvature of 500 feet at that instant. And the friction's keeping him from going up the hill. But if he speeds up and goes faster and faster and faster, he will slide up the hill. So the frictional force is doing this. The frictional force is, and you know where it comes from? It comes from the road surface, maybe asphalt or concrete, I don't know, pushing on his tires, his rubber tires. There's a lot of static friction there. Okay, good. Well, we understand all that. Now let's let's look at the forces on this car. Hey, before we do that though, let me get my green pencil out and let me get some of my really sharp students to help me. We need the tangential unit vector and the normal unit vector. We can't use Newton's second law. We can't find components if we don't know directions. We can't do Newton's second law unless we get one of our students to help us find the tangential and normal unit vector directions. So let me go to my list of wonderful students here. Shane, unmute and say hi.
Hi.
Hey, good for you, Shane. Shane, I need your help. I need your help, Shane. I need to take my green pencil here and I need to put the, let's do the tangential unit vector, Shane. Where do I put the tangential unit vector at the car? There's our car. Where do I put that tangential unit vector?
It'll be coming out of the board towards you.
Man, that guy.
What?
You're right. Shane's right. It's coming out of the board. Now, the way I draw something coming out of the board is I draw an arrowhead. You're looking at an arrowhead. It's coming at you. So we'll just put it like that. That'll work. Here we'll put an arrowhead coming out of the board. Shane's absolutely right. That's the direction of the tangential unit vector. Now, as long as I've got Shane here on the line, Shane, we need the direction of the normal unit vector. Go for it, Shane. Where do I put that?
To the left of the car.
How come you're so smart, Shane? You're not supposed to get these all right. But he's right. See, it's going. Is that what you meant, Shane?
Yes.
To the left? That's it. By Jove, Shane has got it right. He's got the tangential unit vector. It's coming out of the board. Coming out of the board. And then the normal unit vector, it's just going over here like that. Okay. Got to have those really before you can write your Newton's second law. So now let's write our Newton's second law. Is there any question on that? Guys, let me tell you something. If you mess that up and you don't know where those directions are, you're never going to get your Newton's second law right. It depends on knowing those directions. Okay, we're going to do our Newton's second law now. Here goes. We talked about friction there. I'm hoping you understood all that. Hey, but wait a minute, I'm forgetting something. Before you can do Newton's second law, you got to finish putting the red stuff on. Now we have a weight. How about mg? That sounds pretty good. They never told us the weight of the car. That would have been nice, but I don't think they did. So we have the weight of the car. We have friction. Oh, wait a minute. There's a normal force. There's a normal force. It's the road pushing up. It's the normal force. Now, if that car was just sitting there on the hill, the normal force would be mg cosine of theta. But it's not just sitting there. It's moving, it's accelerating. And I don't know how to find the normal force yet. But that's it, guys. There's only those three forces, unless you know of another one. I'm going to open the floor here now. Is there another force that I'm forgetting? Am I forgetting another force? Well, nobody said anything. I don't think there is. I don't think there's another force. I think that's it. I think you have your weight, your friction, that's the force of the road on the tires. And the normal, that's the road pushing up on the car. And that is it. Okay, well, let's write our Newton's second law. Here it goes. Now in the tangential direction, you do have some forces there. You have like air friction on the car. You have There's also friction of the road. But you also have the force of the tires and the motor turning the tires, making you go. But if you're going at a constant speed, all those forces cancel out and give you zero, because see, there's no acceleration in the tangential direction. It's going at a constant speed as it goes around the circle. Now it's got normal acceleration. The acceleration is not zero. The vector acceleration is not zero because you have normal acceleration. But I don't think you have any tangential. Now let's do the normal acceleration. Here goes. Newton's second law in the normal direction. Of course, you know what that's going to be. That's going to be the mass times v squared over rho. Did they give us the velocity? Let me read this. Velocity. Oh, no, we have to, remember, we have to find the velocity. They didn't give us the mass. They did give us the radius of curvature, but we don't know the velocity. But we do know it's that velocity of impending motion. We know that much. But now let's write the forces in the normal direction. Well, here's the normal direction. The weight, mg, doesn't have any component in the normal direction. Because it's perpendicular. But now the normal does. I think this angle is 30 degrees also. And so it has a component of the normal force. I believe it's sine of 30. See, that's the component. I'm not sure about that. Now, let me think about this just a minute. Yeah, I think so, because see, if you broke this into components, I think there's a 30 here. So that's normal sine. Yeah, I believe that's normal sine of 30 going in the normal direction. Okay. I think we, and now see, this friction has a component also in the normal direction. Here's the normal direction and it's got a component. So it's friction, which we could write as 0.2 times the normal. Remember, at impending motion, you can set the friction equal to the coefficient of static friction times the normal. And then we would have to have a cosine of 30. See, there's a 30-degree angle here. And we're after the component going in the normal. So I think that's it on the left. And on the right, what we have is the mass v squared over rho, which is 500, right? 500. Okay, well, I think we're all done with the that equation. Now, how many unknowns do we have? Let's see, we have, holy cow, we have the normal, we have the mass, and we have the velocity. We have, so far we have one equation and 3 unknowns. We're kind of up a creek, aren't we? We can't do one equation with 3 unknowns. We could do 3 equations with 3 unknowns, but not one equation with 3 unknowns. We need another equation, but it's not going to be the sum of the forces in the tangential. That isn't going to help us any because there's 0. But this is one of those problems that you have to stare at for a while. There is another equation. This body is staying in the plane of this big circle it's going in. It's going around and around and around. It's not going up or down any. So if you call this the y direction, just call that the y direction. I think the sum of the forces in the y direction is 0. I don't think it's accelerating. It's not going up or down. So what we're going to do is we're going to write the sum of the forces in the y direction. Well, let's see what we got here. In the y direction, we have, let me scoot that over. Probably going to need the room. In the y direction, we have, hey, this has a component. You see this normal? Can you see it has a component of normal cosine of 30 degrees going up? Yeah. Hey, this has a component, this minus mg going down. And even this friction has a component going down. It's minus friction, which is 0.2 times the normal, sine of 30 degrees equals 0. Okay, now we made a little progress now. We've got 2 equations and how many unknowns? Well, we don't know the normal, we don't know the mass. You know what? This equation's only got 2 unknowns. We don't know the normal and we don't know the mass. We know g. But watch out, they're talking about feet. So g is going to be 32.2. Okay. Why don't we play with this equation and get our let's just do some algebra on this equation. Can you see that you could write, we're doing algebra now, guys. It's algebra time. It looks hopeless because we have 2 equations and 3 unknowns, but we'll just kind of play with it and see what happens. Do this with me. Go normal times cosine of 30 minus 0.2 sine of 30 equals mg. I did a little algebra on this equation. Stare at it and see if I did that okay. I think I did it okay. All right, now put that in your calculator and let's get some numbers on that. Here we go. Okay, here's what I'm getting. I'm getting 0.7660 times the normal equals m times g, which we know is 32.2 feet per second squared. Okay. And will that help us any? Now let me think. I'm thinking and I'm thinking and I'm thinking. Well, I'll tell you what we could do. We could get the mass in terms of the normal. Let's do that. Do some algebra on this and see what we get. See if you get 0.0237 bloody 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 times the normal for the mass. I think so. Okay, now here's my plan. Maybe I need to do it the other way. Let me get the normal in terms of the mass. I'm getting 42.035 times the mass for the normal. I really like this. I really like this because I can substitute that normal in there, algebra students. Let me do that. There's a little bit of room over here. I'm going to substitute that in for the normal. So we got 42.035 times the mass times sine of 30 plus it'd be easier if I combine those. Let me combine those just a minute. Take this and combine these two. Sine of 30 plus 0.2 times cosine of 30. You could write this as 0.6732 times the normal, all of this. So that's what I'm going to do. I'm going to go 0.6732 times this normal, 42.035, m equals mv squared over 500. We're multiplying all this. Hey, we can cancel out those stinking m's and we can find our velocity now. I'm going to shut up and I want you to solve this and get me the velocity. Now this is the impending velocity. You go any faster than that and you start sliding up the hill. But you can go that fast and still stay on the road at that spot. Go ahead and solve for the velocity, and I'll call on one of my brighter students here in just a minute. I'm going to do it. You do it. Gee, I don't know if this is right. Let me call on somebody here. We're going to call on my friend Ryan. Ryan, unmute and say hi.
Hello.
Hey, hello. Ryan, did you get a value for the velocity from that equation?
I got 115.73 meters per second.
This is all in feet, Ryan.
Oh, yeah, feet per second.
But I got a different answer. Do it again.
Okay.
Now those m's, they cancel out, Ryan. See those m's? That's the mass.
Yes.
They go bye-bye.
Yeah, I didn't include them. Did you get 118.95?
Yes, I did. I got
Okay.
118.95 feet per second. Now let's see how we did. This was problem F1310, and I think it was tricky. I go to the back and help me find F1310. And this says 119. The book says 119 feet per second. They just rounded off. We're happy. We were able to do that. Were we supposed to find something else, or was that it? Determine the maximum safe speed. Yeah, we're done. Yay, we did it. And we solved that problem. Do you have any questions about that? Anybody? Well, okay. Okie dokie. Well, let me show you one last thing on this problem. We never did calculate the normal. Well, you can't because you don't know the mass. We never did calculate the friction. Where's the friction? Well, the friction would be 0.2 times the normal. And we never did calculate the weight because you can't do that without the mass. Without the mass, you can't actually get these forces. But I just want to show you something. We could make up a mass. And I wanted to show you how these vectors add up graphically. I know you've done this before, but it won't hurt us any. Let's just suppose the mass is 1 kilogram, or you could have 100 kilograms or 1,000 kilograms. It doesn't matter. I just need a little room here someplace. How about up here? Suppose, do I have time to do this? Because I want to work on other problem. I think so. Yeah, we got time. Suppose the mass is 1 kilogram. There you go. No, wait a minute. Auga, we're in English, senor. We don't want stinking kilograms. What do they use in English? Well, they use slugs. Have I ever told you guys about slugs? I don't remember whether I've told you about slugs or not. But suppose the mass is 1 slug, okay? Then the weight would be 1 slug times 32.2. So the weight, the mg, would be 32.2 pounds. Okay? Because if the mass is 1 and g is 32.2, you get 32.2 pounds. Now the normal is 42 blah, blah, blah times the mass, which is 1 slug. So the normal is 42.035 pounds. And then the friction, well, you know how that goes. That's 0.2 times the normal, which would be 0.2 times the normal. 0.2 times 42.035. Ta-da! I'm getting 8.407 pounds. That's the friction. See, that's the friction. Okay. Well, let's add them up. Let's do Newton's second law. I got enough room right here, I think. Yeah, there's enough room right here. Now, the way you add vectors, they taught me in school many years ago. You put tip to tail, tip to tail, tip to tail. I wonder if they still teach you guys that. That's how you add vectors. So let's just add them. Isn't that what this says? This says take the sum of the vectors. Here, what we're going to do though is we're going to do Newton's second law with vectors. We're going to add vectors. We're going to go sum of all the forces equals MA. Ta-da, there we go. All right, we're going to add our forces. Well, there's only 3, and see, they're red. The reason I want you to write these forces in red is they jump out at you. See there, look, there's 3 red things. That's all the forces there are on this car. And there's no getting lost. Well, let's see, where are the forces? I don't know. If you put them in bright red like that, you can't miss it. Okay, well, we're going to add them up now. Now the weight's 32. Now how am I gonna do 32? I don't. Can't use that. How about we use inches? That'll work. Okay, and it's going straight down now. 32. Here goes. We're going to go straight down. 32. I just went straight down. Well, I'm supposed to go 32.2. Did I do 32 point? Yeah, I kind of did. There's your 32.2 pounds going straight down. Now we have to put a normal in there. Now the normal is 42 something, but it's going that way. I need to put that angle in there. Let me get my protractor here. And that angle, I think, is going to be 30 degrees, isn't it? You want it to be 30 degrees? I think so. Let me see if I can get a 30-degree angle here. Yeah, there we go, 30 degrees. Perfect. Now, how long is that one? Well, it's 42 pounds. Okay, that'd be 4.2 inches. That'll put me right about, not like that maybe. Okay, let me draw that now. I tried to draw that normal. I tried to draw it 42.035 to scale. Oops. There we go. Now we have a frictional force. Hey guys, notice I went tip to tail. See, they call this the tip. That's the tip. This down here is the tail. I went tip to tail. And I see up there, that's a tip. It's the tip of my vector. Vectors have tips and they have tails. Now I need to do this friction. Well, see, this was the normal. Hope you guys understand. This is mg and this is the normal. Well, the friction is perpendicular to the normal. It's always perpendicular to the normal. See, it's perpendicular. And how long is it? Well, it's 8. So 8, that'd just be, that's not much. See, if 32 pounds is 3.2 inches, 8 pounds is just, it's perpendicular and it's about like that. It's not much. Puts me right about, there we go. There's your friction to scale. Now what is what does Newton say? He says if you add up all the forces, and I went tip to tail, tip to tail, tip to tail, you should get the mass. Well, we picked one slug for the mass. So the acceleration should be, did they teach you in school, you go from the tail of the first one to the tip of the very last one? That's how you add vectors. You go tip to tail, tip to tail, tip to tail, and then you go, here, I'll put this one in red. Then you go from the tail of the very first vector, which is right here, to the tip of the very last vector, which is right here. All right, we're going to do that now. And we'll put an arrowhead on that. And you know what that'll give you? That will give you the sum of the forces. It'll give you the sum of the forces. And guess what? The sum of the forces is going in the same direction as the acceleration, because this is just a scalar. It's 1. 1 times acceleration. So it's accelerating. That core is accelerating. And if it's going in a circle, they have a name for it. They call it centripetal acceleration. But that's the sum of the forces. And I can tell you how big it is. I can tell you how big it is. Well, we could get it from here. We know the normal. It's 42. We know the mass, it's 1. We know the velocity. Well, where did the velocity go? Was that the 118 that my wonderful student got for it? No, it was 119. Yeah. Let's plug this in and get our amount. Here we go. It's 0.6732 times the normal, which is 42. 0.035 equals, well, that's it. That's what it equals. Of course, it will equal this too. If you plug in 1 times 119 squared and divide by 500, those should be equal. Let me see what it is. 0.6732 times 42,035. I'm getting a 28.3. This should be 28.3 pounds. But this should be 28.3 pounds also. Let's try it. 119 squared divided by 500. Boy, Juve, I get 28.3 pounds on the right, and I get 28.3 pounds on the left. Newton's second law. So when we measure this, we did it to scale. It should be around about 2.8 inches. Well, let's see what it is. Well, boy, Juve. I don't know if you can see that, but I can. It's less than 3 inches. See, 3 inches is right here. You might be able to see the 3. It's about 2.8 something inches, and by Jove, it works. So see, this is called checking your work. I think I mentioned that a few semesters ago. We went on a campaign for students to check their work. I think it's a good idea. Okay, well, if you fell asleep, I'm sorry, but we finished with that problem. I forget which one it was. It was a problem F. 1310. And we're going to move on to the next problem unless you have a question. Well, we have 12 minutes. Let's move on. Unless you have a question, I'm going to erase all this. But wasn't that fun? We're studying Newton's second law. Okay, well, I'm going to erase all this, and we're going to do another one now. Okay, now the one I wanted to do now is this one here. This is 1361. We're going to do 1361. Now, this is not on your homework list, is it? I don't want to do your homework and spoil your fun. 1361. 1361. I don't think so. No. I don't think so. No. So let's do it together. That'd be good. We got time. We'll go through the steps. Now, in this one here, there's a boy on a swing, and he's swinging back and forth. He's momentarily at rest. Okay, and he's at a 60-degree place. Okay, well, let me draw that 60-degree place that this boy is at. Here we go. I need a 60-degree angle here. 60-degree angle, yeah, here we go. Puts me right here, I think. Yeah, that's pretty good. Yeah, I actually measured that 60-degree angle there. And here's your boy now. Now he's in a swing and he's, I don't know, yeah. There he is. There's your boy. Now, how much is the boy, his mass? Do we know? Center mass. I'm reading it. I don't think, oh yeah, he's a 60-pound boy. He's a 60-pound boy. So this angle happens to be 60 degrees right now. But you know what? He's gonna do that, isn't he? See, he comes up here, he stops, and then he swings, and then he'll stop. He'll swing down. He'll swing down here, and then he'll stop, and then he'll swing back and forth. Okay, that's what he's going to do. 60 pounds. And they want to know the tension. He's actually got 2 ropes on him. So we could figure out 1 rope and divide by 2 if he's got 2 ropes. And what else do we know? They want to know the speed and the tension when he's down there at 90. See, he's gonna come down here and go faster and faster. And when he gets down here to 90, artist rendition, there you go. He's going to have a velocity. They want to know what it is. Determine the speed and the tension. All right, well, let's see if we can. Here, I'll put I probably shouldn't use red for velocity, though. I like red for forces. So here, let me just put the velocity like that. There's the velocity. There we go. So he's going to have a velocity down there. I think it's time to put the red stuff in. Okay. In general, wherever he is here, he's going to have an mg Well, that's 60 pounds. You don't multiply 60 by 9.81 to get his weight. It's already given. It's 60 pounds. So that's, can you read my writing? So we got his weight. It's 60 pounds. All right. How are we doing on time? Oh, we only have 7 minutes. But we can do a lot in 7 minutes. They did a lot in that Kansas City Chargers game, didn't they? 58-yard field goal. Huh, that's a pretty long field goal, isn't it? Anybody watch that game? If you watch that game, speak up. No, nobody watched it. You're too busy doing homework. You're busy studying. Good for you. Good. You shouldn't be watching football. You should be studying. Good. Okay, now wait a minute. That's not the only force on that guy. You're going to have a tension here. But I think that's it, guys. There's just those two forces. There's tension and the weight. And, I know what I need now. I need green stuff. We might not make it through this problem. We only have 5 minutes. But you can do a lot in 5 minutes. I'm going to call on somebody, and what I need is the tangential and the normal unit vectors. Okay, let me find one of my very best students here. Jesus, unmute and say hi, or you could say hola, whatever. Jesus, Earth calling Jesus, come in, Jesus.
Yes, what's up?
Yeah, good.
Sorry.
Good to hear from you. Jesus, I need your help. I need to know. Here's this boy right here. We're going to put the tangential unit vector on this boy right here with your help. Where did I put it?
Well, wouldn't it kind of be down to the right?
Yeah, he knows. He knows. It's Jesus. We know that this is in the direction of the motion.
Yeah.
Now, Jesus, we need the normal unit vector. Where is it?
That'd be 90 degrees counterclockwise. So it'd kind of be top right.
It's going up like this, isn't it?
Yeah, kind of along the line.
Boy, he understands. He's got it. Good going. Okay. Well, let's write the Newton's second law. We've done our homework now. We've done the red stuff. We've done the green stuff. You really can't do Newton's second law until you've done those two items. And let's write the sum of the forces in the tangential direction. And in the tangential direction, the tension doesn't have any component. But the 60 pounds does. It's 60 pounds times, now let me think about this. I think it's well, there's a 60 there. See, this has components. It's got a component this way and this way. I think it's 60 cosine of theta. If this is theta in general, I know it's 60 pounds in the picture there, but if it's theta in general, then that theta is right there. And the component in the tangential direction is 60 cosine theta. Okay, that's it. That's it on the left. And on the right, we have the mass. Oh, but wait a minute, to get the mass, you have to take 60 and divide by 32.2 to get the slugs. So there's the mass in slugs times acceleration, which is v squared over 10. They said this is 10 feet. 10 feet. V squared over r, 10 feet. Okay, so we have a lovely equation here. No, wait a minute, this is wrong. This is wrong. No, this is times v dot. I got mixed up there. Somebody could have jumped on me and gotten a thank you point. See, in the normal direction, you have a v squared over r, but in the tangential, it's v dot, isn't it? Okay. Or another way of writing that is just AT. That's the tangential component of your acceleration. Oh no, we're out of time almost. I have 2 minutes left. Let's see what I can do. Okay. What am I trying to do? Anyway, I'm trying to get the velocity. Don't they want the velocity? Let me read this. Yeah, the speed. They want the velocity. They want the tension. But to get the speed, well, we could get the acceleration. Well, let me write it. I have a minute and a half. We might be able to get the speed, and then I'll be out of time. It's sad. Do a little algebra with me here, and let's see what we get. 60. You know what? The 60s cancel, don't they? They just cancel. And what you wind up with is 32.2 cosine of theta. Now, as you move along this path, AT ds is equal to V dV. Do you guys remember this equation from when we were all younger and better looking? Remember that equation? No, you don't. You've forgotten it. Well, I'm going to have to speed this up because I'm running out of time. ds can be written as, see, that's just the distance that you travel along. ds can be written as 10 feet times d theta. Remember s equals r d theta? Well, ds is equal to r. S is equal to r theta, ds is equal to r d theta. So you could write this ds as 10 d theta. And then you got v dv. Oh gee, we're gonna here. Let me show you what to do, and then you can finish this problem. You're gonna have to integrate both sides. You're gonna have to go from 0. If you want to know the velocity when it gets to 90, you're going to have to plug in, not there, you plug in the 90 here, and here you just plug in the v. And I know you can do this. I know you can take the integral of a cosine, and I know you can do that. Oh, it's sad. But I know you could do this, and you could get the velocity. And once you had the velocity, then you could write your sum of the forces in the normal direction, Newton's second law, and get your tension, but it's sad. Have you ever noticed how fast time goes when you're having fun? But we're going to have to quit. You guys, I'll see you on Wednesday at 9:30. Enjoy your homework, and we'll say bye-bye for now. Goodbye. Somebody say bye. There you go. See you guys later. We enjoyed it.